Hey, CS302 class, so here's our assignment 5, and the title is Hungry for Red Apples, a very famous slogan that Jerry pitched to his, I don't know, he works at sales, I think. I'm not sure where he works, but he pitched this idea, and he ran this in a very state-of-the-art simulation, and of course it worked there, but in real life it didn't really work out, which I guess is what it is. So basically, this program, I guess. So I suppose another simulation comes up, and now in this simulation, we had to write a program to help Jerry find all the red apples in a binary tree. So, which makes sense because there are there are apples that grow on trees. So this actually makes perfect sense to have a binary tree sort of implementation. So what you want to do in this program is you want to find the minimal path needed to retrieve all of the possible red apples on a binary tree. So I'll go over the main type of algorithm towards the end of this video, but for now let's go over just the class that we have right here. So here's going to be our bin tree or binary tree class. So of course we have our struct bin tree node. Now, luckily, this is not going to be a templated program, so it does make the process a bit easier to implement this. So, of course, you could have a header file and separate it to a separate implementation file if you want. But, of course, you can have everything all in one header file as always. So, in this class, we have this struct bin tree node. So, every bin tree node has a left and right child pointer and a boolean for the apples. So, I'm guessing each node will be an apple on the tree, and I suppose if this apple contains true for Boolean value, then that node would be a red apple. If it contains false, then it would not be a red apple, I guess is how we can think about this. So each element will be of type bin tree node, and then we're going to have, starting from our private members, I'll talk about this root over here. So basically, bin tree node root is going to be just a root pointer of our binary tree, nothing too fancy there. And now let's go through the rest of our class members. I guess I'll go from the public members. I want to first go over the root private field, but let's go over the public members. So first we'll have our default constructor, bin tree. Basically, this constructor will just set root to be null. That's all it does. It initializes an empty binary tree. Now, this second constructor is going to pass in a vector of booleans. And it's going to contain these true or false, as you have to construct a binary tree from this vector. And you're going to actually call this function build tree. You're going to call this function build tree within our constructor. So I'll go over the actual logic of how we can think about this in a bit. Then we have our destructor, which deallocates a binary tree. This destructor is going to essentially call a function destroy tree, because to deallocate a tree, you have to run this recursively. So I'll kind of give an idea of how you want to write the destroy tree function in a bit. And of course, we're going to have our minTime functions, and we have the one that's called in main essentially. Then we have our sort of overloaded. We have our wrapper. This is going to be our wrapper function right here. So we're going to simply just call this function inside of this minTime function. It's going to retrieve the minimum number of steps needed to retrieve all the red apples from our binary tree of apples. So now I'm going to discuss how to construct the tree given the input or given this vector of booleans. Okay, so this is the vector you're going to be passing into the function, or sorry, to the constructor that takes in the vector. You have to create this tree given this vector of booleans. Now the file that I gave you has these falses and trues separated by a space. Now the main that I provided for you actually has this code that reads that file and constructs this vector. So that's already given to you. So you can assume you have this vector given to you. You have to create this, basically, is the idea. So the idea is how we can look at this as this very topmost element. This index 0 is going to be the root element. And then this element right here is going to just be that element right there. This element right here is going to be this element in our tree. Then of course, this element is going to be that element. And this one will be this. And then this element in the vector is really just this element in our tree. And then this last element right here is going to be this element in our tree. So that's basically sort of the very quick view of this. Let's go ahead and go into maybe a little bit of implementation as to how we could sort of construct this tree recursively. Alrighty. So when you first call this, when this constructor is called in main, initially pass in this vector. So in that constructor, the first thing you'll do is, since this vector is not empty, you're going to take this root pointer and you're going to allocate a node to it. So I'm going to go ahead and just put this right over here. And we allocate a node, so root will point to this new node. And of course, index 0, that's going to be the root element. So I'm going to take the element 0 and write that into that, that apple field of that node. So I'm going to put false right over there, just like that. Then of course, you want to make sure that you set this node accordingly, because remember, this node is going to actually be currently a leaf. Now, of course, you're going to maybe expand on this node, but right now, at this moment in time, this node is going to be a leaf node. So make sure you set this node's, left and right child pointers accordingly. Okay, once you have that, we have a function in our handout. Let me just go ahead and check this out. We have this function called build tree. This function will take in a parameter r, our vector, and an integer. So r is going to point to some node in my tree. This will be just this vector that's passed into this constructor. And then this integer is going to be the index of which element in the vector we're currently going to expand on, because we have to constantly retrieve elements from our vector and store them into our nodes sort of one by one. Okay, so now that we kind of have the build tree function, we have to go ahead and call build tree. The first thing we'll do is, after we create our root node, we pass in the root into this function. As always, you always start from the root, pass in the root, pass in the vector, and we're going to pass in 0. Because we're going to start from index 0, we're going to move from that point on. So what's going to happen is, r is going to point to that root node, I is going to be 0, and of course the vector is just going to be always just that vector as always. So now we're currently on this node right there. So I have to be able to figure out which indices, which elements in this vector is going to be the left and right child. Well, from just eyeballing this, it looks like this element here in blue would be the left child, and this element here, I guess maybe in pink or violet, I think it's pink, this is going to be the right child. So what we have to do now is, well, we have to allocate, I mean, it's up to you. I didn't do it quite like this, but this way it does actually, I think it does work as well. You want to allocate a node here, these two nodes, and you want to set these two accordingly, and you're going to write false and true right there. So now you allocate these two nodes. Now you have to recursively expand, because this node, so these two nodes right here, so this is like the left child, and this is the right child, these also may have additional children. Looking at this vector, index 1, well, which element is going to be its left child? I mean, I don't want to really give it away, but I mean, I hope it's kind of not really that obvious, but you may have to do some type of a multiplication, maybe multiply it by 2 and do some other things to be able to take an index, any index in the vector, and be able to determine which element at some index, which one is the left child, which one is the right child. You have to know that, basically. So you want to first figure out, so what you're going to first do is, well, you're going to just basically call the function recursively, and call build tree. You're going to pass an R arrow left into the function. So what's going to happen is R expanded right there, and I is going to be 1 in this function called instance. So now we're going to be at this level, and now we have to figure out the 2 children for this node at index 1. So looking at this vector, we have to take this index 1 and multiply it by 2 possibly to extract the next child. Because if you look at this over here, remember we had, let's say, false and true. So, I don't know. It's almost like indices 3 and 4 are 2 children of 1. And it looks like it's, I have to maybe do some addition, add by 1, multiply by 2, or multiply by 2 plus 1. You have to just, maybe just experiment with those a little bit and figure it out. But you have to first extract the 2 children indices so you can allocate those to the left and right child pointers of this node and expand on it further. Now, at some point, if you go beyond the bounds of the vector, then you hit a base case. You want to return back up and then get out of this function. So this looks to be almost like a pre-ordered type traversal of our binary tree. So you figure out, so your index I tells you which element you're currently looking at, and you have to expand a left and right side by taking the index you're currently on, figuring out which elements are the left and right children of this index, assign the 2 nodes to R's left, R's right, and then of course recursively expand on R left and R right until you go beyond the bounds of the vector, then you turn back up and all that. So I hope this explanation did kind of help. So the last, I guess sort of not the last, but sort of the last complicated step is going to be being able to traverse this tree and, getting the min number of steps needed to extract the red apples. Let's go ahead and do that next. All right, so now let's go over the minTime function. So this minTime right there is going to simply just be called in main. It returns that value back, which I'll explain in a second. And this function, minTime, is going to internally call this recursive function. So simply, this function int minTime with no parameters, the whole function body will just be return minTime root comma 0. That's all you're going to do. This function recursively is going to, I guess you can say, magically will go ahead and construct our solution. Let's go to our example tree and make sense of this. So the solution to this problem will be the following. So we see here we have a red apple here. So I guess I'll circle these 2 here. So we have 1 red apple right there and 1 right there, like that. So what's going to happen is in this example, we start off at 0. So we took 1 step to reach this spot. Then we have, so I'll draw an arrow like this. Then our second step goes over there. We saw a red apple. We go back. That's 3. Go back to root. That's 4. That's 5. And then that's 6. So with 6 steps, 6 movements we had to do to be able to retrieve these 2 red apples. So that's the solution for that tree 01.txt. That's our solution. So we have to figure out, well, how in the heck did we get that? Because that seemed awfully suspicious and it was too much magic, actually, to the point where it doesn't make any sense. But that's what we have to do. Now, we're going to obviously have to expand every possible path, but we only want to preserve the paths that actually led to a red apple being discovered. Because this method is kind of very simple. You want to go ahead and find, well, what's the actual recursive step or recursive sort of way of thinking about this. So of course, when you first call the function, we start off at 0. So what's going to happen is that parameter, that integer parameter we have in that function minTime, that's going to be a counter, if you will. That's going to be that parameter that stores our current counter. So what happens here is when we go ahead and we start the root over here, we're going to jump to the left first, and then our index, our counter will now be 1. And then we're going to jump over here. Whoops, be consistent. We jump over here next. Our counter is going to be 2. And then we hit a null. Now, since we hit a null, and along this path, we actually did not reach, or did not really see a red apple. So let's look at the parameters once again for this function. So for minTime, we have to determine that, okay, this integer, this argument right here, this second integer is going to initially be 0, then 1, then 2, then 3. It's going to be those values basically. This integer, we're constantly passing in sort of, you can say, plus 1. It's kind of similar to, I think, let me see, I think it was similar to that Knight's problem. So we're passing in constantly these values like that. We hit this case null, and as we work our way up the tree, we want to go ahead and see, well, did we reach the red apple? Well, we didn't, so at this stage, we return back, the value 0 is returned back. Because along this path, we didn't really reach a red apple. And now if we go over here, we're going to pass in 2 into this function as well. Because when we had r pointing to this node right here, which I'll just circle this here in pink, that parameter was a value 1. Oh, darn. So what happened was we passed in 2 into this function, but we returned a 0 back up the tree because we didn't find a red apple along this path. So this path right here didn't lead to red apple being discovered. Now over here, we have a red apple found, which is great. And now we're going to go to, we're going to call a function again, right here. And we're going to pass in r equals null. So I guess we can return a 0 back up because 0 is, there's nothing here. And we also have to call a function on the other side as well. So I guess I skipped it on this example right here. When r pointed to this node right, they were supposed to have called a function on both the left and the right. Both led to a null, so nothing happened. It returns a 0 in both cases. So what happens is we return a 0, but right here, we're on a red apple currently. So in the other path, I returned a 0, but here I don't want to return a 0. Because here what happens is, well, we have red apple discovered. So I want to return a value 2 instead, actually. Implying that, actually, no, sorry, we're going to turn a 3. Because, well, this direction, we actually did reach a red apple. So we have to first go from this, we had to first try this, which is 1. Then we went over here, 2, and then back, so it's 3. And then since, so what happened is since the function didn't return a 0, that means we know for sure in that path a red apple was found. So when we go back to this function right here, where r points to this node right there, so since that red path returned the value 3, not 0, that means we know for sure that that right side path had to have led to a red apple being discovered. So we can very easily check the return that the recursive function gives us back to the parent. The parent returns a 0, that means, okay, on the way up the tree, we did not really find any red apples. But if, let's say, it returns a non-zero, that means we know it returned a red apple. So we have to go ahead and return a 4 back up. And then from here, we're going to have to basically call a function, because now at the root level, we called minTime on the left side, and you have to call the right side. So you have to go ahead and jump our R pointer over here. And we're going to pass in the value 5 into this function. Because, well, there's a chance we could find another apple along this way. So then we go ahead and we call the function again right here. And we pass in the value 6. And then we hit a null. And then on the way up, we return zeros. Because on the way up, so from this node where R points to this node right here, kind of hard to see on the screen, this node right here, there was no red apple discovered right there. So we return a 0 up the tree, up to the parent. And same idea here, both of these return zeros because neither of these two nodes at the very bottom are in fact red apples. But we return back to the node right here. Then we see here this node is a red apple, so we return 6 up to the parent. And then we return 6 back to main. It's a very odd recursive scenario, but we constantly increment by 1 as we move down the tree, and on the way up, we start checking to make sure that that node contains the true. If it does, then we're going to return that counter plus 1, otherwise return the value 0. If it returns 0 to the parent, then the parent knows that either the left or right side, whichever side we took, whichever path we took at that moment, we know it led to either it discovered 1 or more red apples on that path. It returns a 0 back to the parent. That means the parent knows that that path that it took, the left or right path, had to have led to a 0. So a little bit odd, but this is kind of the this is sort of the idea for this algorithm, I suppose if you can say. Now, this is a very simple example, but this doesn't really. You have to also figure out. I think what I said does sort of has some hidden, content there. But let's say we have multiple red apples along the way. This actually, you have to also make sure you handle that as well. Now, I think what I went over a second ago does cover that case as well, but you have to write the code to figure that out. So basically, you really have two indices or two integers. One being passed into a recursive function, which keeps on counting by 1, and then one that returns back to the parent, and a 0 and non-zero kind of gives the parent a clue as to what happened along that path. So that's all I'm going to say for right now. So I guess that's like the main important algorithm. So the next thing I'll talk about is going to be deallocation, or deallocating our entire binary tree. Okay, so here's our tree, and I wish to deallocate this tree. So the destructor is going to basically, let me just bring up the PDF. The destructor we have right there is going to basically, it's going to call the function destroy tree, and it has a pointer. So you're going to, of course, initially pass in a root pointer into this function, and you're going to have to really just do a post-order type traversal, because here's the idea with this. If let's say initially R points to this node, if I were to go ahead and say delete R right now and deallocate this node, then the problem is R becomes a dangling pointer. So of course the next step would be, of course, after you want to then deallocate the whole left subtree and then the whole right subtree. So the idea is, well, this method is actually kind of risky, because if you do it like this, what can end up happening is R is going to be a dangling pointer. So you have to basically, you have to do essentially a post-order type traversal to deallocate our tree. So to do this, we'll do the following. What if I told you you want to first deallocate the whole left side? So I don't know, call the function destroy tree and pass in our arrow left. And of course, it's going to magically deallocate this entire side first. So what's going to happen is, of course, if r equals null, return, else, you're going to first deallocate the left, then deallocate the right, and then delete r, basically. So for every node, what's going to happen is, as you move down the tree, so r left in this situation would be null, return back to this bottommost node right there. Then we go ahead and call destroy tree pass an r arrow right, which will be also a null. Return back immediately. And then we're going to deallocate this node and return back to this function, which we're going to go ahead and call destroy tree and pass in r arrow right, which is right there. And then we're going to go ahead and we're going to call destroy tree pass an r arrow left, which is going to be a null. So return back immediately back to this node. Then we go ahead and call destroy tree pass an r arrow right, which will be null again. Return back up to this tree. So now where r points to this node right here, we deallocated the left and the right. We have to now deallocate this node, return back up to the parent, and r points this node right here. So at this level, we deallocated this node's left subtree and right subtree. Now I deallocate r and move up to the top. So right here, we deallocate the whole left side, and now I have to deallocate the whole right side and then deallocate r. So it's going to be a post or a traversal. It's going to be literally post order, except instead of saying just C out, r arrow, whatever, you're going to have delete r. Is going to be that post order work. Hopefully this picture here helps you out. So that's basically the assignment. So a few more things to add. You only have to submit just your binary, your bintree.h. And if you have your header file separated from your implementation file, then you would submit your header file, so bintree.h, and then bintree.cpp, and that's it. You're given the main. You have to upload the main because main is given to you in CodeGrade. And you must submit a file called bintree.h because the main that's provided on CodeGrade actually includes a file called bintree.h. If you don't name your header file like that, it will not be able to locate that and won't be able to compile the main. So implementation file can be whatever you want it to be, but the header file must be bintree.h. So that's pretty much it. So hopefully this video did help you, and I guess till next time.